Aki has the unbreakable will to get rust to the metal, to mill it into shapes snappy, make customers happy, though this battle is somewhat uphill.
Thank you very much. Good day, everybody. Thank you very much for joining me today. My name is Aki, and today I would like to share some of my experiences using Rust in metal fabrication. Let's get started. And of course, I'm not referring to this kind of oxidized kind of rust, which is generally not very desirable in metal fabrication. The oxygen in the air reacts with iron to form the colored, structurally weaker substance that we refer to as rust. In metal fabrication, various techniques such as painting and plating are used to protect the steel from rusting. And today, I'd like to explore some uses of a more desirable kind of rust, the Rust programming language, and share some of my experiences using it to develop enterprise software. Today's talk will be a primarily non-technical perspective on using Rust in the development of enterprise software and the implications of such a programming language selection. So, what is metal fabrication anyways? Well, it refers to the manufacturing process that gives us these goodies in life. Large parts of this Ferrari are made from metal. The body paneling is made from giant sheets of metal pressed into the beautiful aerodynamic shape. And the engine blocks are effectively carved from large blocks of metal. The exhaust pipes, the hubcaps, are all created through metal fabrication processes. It also brings us the metal factory equipment that bottles our beloved Coca Cola drinks. It brings us uh, the belt conveyors that run the Amazon warehouses, that brings us the boxes to our front doors. And of course, our beloved gaming rigs with the metal power supplies and the cases, all made out of sheet metal, bent and cut into just the right shapes. So, let's take a look at what the processes are that are used to modify the raw metal into these goods that we know and love. So I did what anybody would do and asked Google image search what metal fabrication was. As you can see, a lot of metal and lots of sparks. On the right here, we see a welder. This is a process known as welding, where metal parts are melted to form one solid block. Here with more sparks, we see a laser cutter, which uses high-intensity laser beams to physically cut shapes out of sheets of metal. And as you can imagine, these are very expensive, high precision machines. And optimally using these manufacturing equipment is very, very important to the success of any manufacturing operation. So the metal fabrication industry benefits quite a bit from the use of software to run the business. Software is used throughout all phases of metal manufacturing, from design and simulation on the left, all the way to final delivery on the right. In design, we have CAD 3D modeling. CAD stands for Computer Aided Design, where the end product is designed on the computer using simulation tools for aerodynamic testing and whatnot, as well as something that we software developers know as version control, the equivalent of making sure that various iterations are tracked and the differences can be seen. Once the design is complete, we need to go and purchase the raw materials. This requires the exchange of money, that requires approval workflows and integration with accounting systems. And once the materials are in hand, then we need to make sure that we utilize these expensive resources, the manufacturing equipment, and scheduling workers and the machines to optimally plan the manufacturing system. Once the actual product is created, we need to deliver it to the end customer, which requires equipment like the forklift shown here. We need to track inventory in the warehouse and also make sure that we know when it's finally delivered. Most of the information in today's talk is based around my experiences developing the right-hand three: purchasing, manufacturing, logistics, and developing software for these areas. And these three areas are created primarily when, when, when we organize that information to streamline the workflow, to enforce data integrity policies, and track the flow of the physical goods and the money. So, a brief overview of the system architecture. My development team builds enterprise software that uses the browser as the primary user interface. And so our architecture looks very much like a web application with a front end and some back end processes. But one of the most important things that we've done is in enterprise software, the domain is very complex. And so by separating out concerns into these separate modules, we've been able to achieve a higher level of development efficiency. On the left is the front end, which is designed to optimally present data to the customer or the user uh, in the task that they are doing right now. The BFF, the backend for front end, is a TypeScript Node.js process, and its role is to fetch data from wherever the data is, whether it's another API, another system, a third-party API, whatever it is, its job is to go and get the data. And finally, the backend. This is written in Rust, and its goal is to enforce the domain model and to maintain data integrity. And this is the area that I would like to talk about today. First, I'd like to cover some of the technical aspects of using Rust. Specifically, using Rust in the domain-driven design sense. And second, our impressions of the library ecosystem. Domain-driven design is one of the most important concepts that we value in the development of enterprise software, and it's a term coined by Eric Evans in his 2003 book. And it emphasizes the importance for software developers to understand the real-world domain and try to model it and express it in software. So, as an example, in metal fabrication, we use paint to prevent rusting. Given the various kinds of paints and colors, let's try to create a data structure to express the color of paint in Rust. So RGB is a way that we use often in web development. And let's say that 8-bit colors can be used, and so we have a tuple of three 8-bit numbers. Taking another domain, such as printing, we may need to use CMYK. So another expression of color with a different set of tuples. And coming from C++, this if this way of expressing kind of typed unions in Rust has been incredibly powerful. But as with all things in the real world, things weren't as easy as they seemed. We found that in certain areas of the industry, our customers did not know what color they wanted. Well, to be specific, they were not able to give us an RGB or a CMYK value that they wanted. They actually had a color sample, a physical product they had made previously, and they wanted the same color as that. And so as an industry and as a manufacturer, we needed to make sure that our enterprise system, which was already in place, be able to handle this new kind of way of specifying color. And so Rust's enum allowed us to just do this, create a way to express physical color sample. Of course, there's other ways to expand on this, but this was actually a fairly simple way for us to know that there was no specification, that we actually needed to get the actual physical color sample from the customer. And handling this color is also quite easy. With a match statement, we can easily decompose each of RGB or CMYK and utilize those appropriately. And as with all things where the domain is constantly evolving, the Rust compiler and the ability for the match statement to tell us when we're missing things, this has actually saved us many, many times. Here, the commented out line for physical color sample in the match statement would generate a compiler error. And so if somebody modifying the domain model or the actual struct did not realize all the places where it was being used, we could simply ask the compiler to detect it for us. The next aspect after enums that we have utilized extensively is using phantom data types as markers for compile time data type checking. So we use money in enterprise and we use multiple currencies. And so if we were to have a money struct here, of course we'd have an amount as some kind of decimal value. And the currency itself could be held as some kind of string. But that would require us to do runtime checks, which are of course sometimes necessary. But when we have business logic coded in, we often want to have compile time checking. And so by using phantom data types here, we can create some enums for a Japanese yen or US dollar so that when we create a statement like this, where we try to add a Japanese yen to a US dollar, we would get a compile error like this, a very, very friendly compile error that tells us exactly what happened. This we use not just for monetary types, but also for physical types, such as meters, length versus volume versus area. It doesn't make sense to add volume to a length, for example. And using these kinds of phantom data types has helped us extensively and optimize our development process. Next, I'd like to talk about some of our impressions of the library ecosystem. The good parts. Uh, we actually found very high quality coverage across our needs. We use RabbitMQ for our event bus, Redis for some caching, PostgreSQL for, for data persistence, and gRPC for communication purposes. Here, we've listed some of the libraries that we've used, and we have found incredibly good experiences with them. As for some of the wishes that we had, it would have been great if we could find more production use cases, because production ready can be a very, very subjective term. But the real world, um, using a real world product as an example really adds concreteness to it. And so, for example, we started using Tower gRPC because Linkerd was using it. And of course, we started using Rust in version 1.35, which is pre-async await. And so when async await rolled around, we weren't quite sure if we should jump on the bandwagon right then. And in the end, we actually still do not use async await. We just horizontally scale until we can handle it. And so some guidance as to where the async await story is going, I think would be really, really useful for us. And we're definitely watching the community and seeing where things are going right now. Um, and finally, I'd like to cover some things that are non-technical. Primarily, hiring for Rust with new engineering training once new engineers are onboarding, and also how to maintain a good community within the development team itself. And finally, a bit about the community work. Deciding what qualities to look for in a candidate when your technology stack uses Rust is incredibly challenging because it's such a bleeding edge technology. And it's so new that compared to other languages that have been around for a lot longer, it can be hard to figure out what to write in a job description. And so here in Japan, one of the ways that we have decided to do hiring is to look for the core aspects of what are the attributes that make somebody a good Rust engineer. And so for us, what worked and what has worked for the last year or two is the familiarity with a type system with traits and generics, or something that's resembling traits or generics, such as Java or Haskell or TypeScript, as well as various notions of functional programming. And finally, familiarity with computer architecture and memory management, and low-level aspects of how programs run. Of course, if somebody had all three of these aspects, they probably already have touched Rust a little bit. But we have found that many engineers from other languages have been very, very successful using Rust in the development of enterprise software with us. And it was because of their strength in one or more of these areas. And as with many engineers, we don't write code just to write code. We write code to make good things, to make a change. And so, from a hiring perspective, Rust is certainly a distinguishing factor, but enterprise can be kind of a black box. And so, we've made a lot of efforts to make sure that people know what we make using Rust. What is Rust being used for? And how are we optimizing, for example, the metal fabrication supply chain using Rust? And once we have new hires, training them has been required new kinds of efforts because sometimes relearning new foundational concepts, but also learning to talk with the compiler. We have found that once people get used to talking to the compiler, they don't actually need very much handholding. Um, they'll just get up to speed very, very quickly. And finally, Rust is good at some things and not as good at some other things. And so making sure that everybody's aware of how our development team uses Rust and where we choose to not use Rust. For example, in the development of front end, it's probably much easier to use React than to use Rust. And as a development team, having a critical mass of Rustaceans has been incredibly important because it allows us to create a Rustation community within the same development team and fostering a culture to stay up to date because the ecosystem is constantly changing, the language is always evolving. And so we have found that fostering this kind of culture has been very, very important to the success of using Rust within our development team. And finally, the success of the Rust community contributes to the success of the business and the success of our development team. And so as a enterprise software development corporation, it's important that we participate in the community. And so with the pandemic here in Tokyo, a lot of things started to shut down in March. And so in April, we started a meetup, an online meetup called Shitamachi RS in collaboration with Layer X. Because as corporations, we often have some resources that the community does not have access to. And so we believe that it's really important to keep the community alive and making sure that there is constant innovation and that people are always engaged. And with that, um, I'd like to give a few closing words about using Rust in metal fabrication. Metal fabrication itself is a very, very complicated real world domain, but Rust has been an amazing language for developing the software. And the library ecosystem maturity has been actually good enough for us, but at the beginning, it was a bit difficult for us to gauge. And using Rust itself has been technically an amazing experience. And from a non technical perspective, different kinds of efforts were required for hiring and training to maintain this kind of efficiency in our development. But the friendly and welcoming community has been absolutely wonderful. The resources are available in Japanese as well. And so, as my last words, let's, as corporations and as any enterprise user or as any commercial entity, think it's really, or actually any development team for that matter, I think it's really, really important to share real world use cases of Rust and to really support the Rust community because the success of the community really gives back to the success of every project that we work on. So, thank you very much for your time today. It was a pleasure.
Thanks, Aki. If you have any questions, please leave comments to the chat. Anyway, there are some questions. Aki, do your Rust structures touch or mirror your TypeScript types in your BFF layer in any ways?
Yes, thank you for the question. The Rust structures are reflected in the TypeScript layer, in fact. It requires, we use gRPC in between, and so we can share some of the gRPC protobuf definition files so that we can easily translate them to both sides. However, of course, the type systems are not exactly the same in Rust and TypeScript. So there's a little bit of massaging that we need to do to make sure that we can handle it. But both Rust and TypeScript have fairly similar notions of types in some ways. And so that has been very instrumental in optimizing or to reduce or to increase the efficiency of our development process.
Any other questions? Okay. Thank you, Aki. That's all.
All right. Thank you very much.
Okay. Thank you very much.